Hello, thank you for having me. Today I'm not only talking about Cinco Cloud, but also about a new feature inside of it, live metamodeling of graphical DSLs. And yeah, sadly my colleagues couldn't be here, so I'm doing this mostly alone. But so what is Cinco Cloud? It's a holistic web-based language workbench, of course, to create graphical languages. And hopefully use them immediately. And but this is not what Cinco Cloud only is about, so language engineering new graphical models, but also provide them to domain experts to directly use them. And for this whole thing to work, it also provides some extensive user project and access management. And so obviously, there are 3 steps always if in the language engineering process, like first design a language. For this purpose, we have 2 meta DSLs, the MGL, the meta graph language, which where a language engineer can specify the abstract syntax based on nodes, edges, graph models, and so on. And the meta style language to specify the concrete syntax, so how these nodes, edges, and so on look. And to add some semantics to the whole story, we just use TypeScript and deliver some interfaces for that. And after that, a language engineer can distribute the graphical language. This is the 2nd step. And the 3rd step to the user or domain expert can use the graphical language to maybe model their own new applications. So the whole project is separated into several modules, 3 modules. First, the main service, which handles all the extensive user project and access management, and also handles the spawning of new workspaces, which are Docker containers, so it's like a mini Azure, if you may think like it. It's based on Kubernetes, and to upload and download new languages into workspaces, we use Min.io. And inside this main service, are of course the language editors or modeling editors, depends on the perspective, which role you take, language engineer or domain expert. And these are just used for the whole file management and so on, and also to write your abstract and concrete syntax. And the technologies we use are Thea, Langdev, and TypeScript. And in theory and also practically, this language editor, apart from this whole main service, is also available as a single Docker image. So if you would like to use it, you can also use it separately from our GitLab. And inside this language editor, the 3rd and last module, of course, is the modeling canvas based on GLSP and Sprotty. GLSP uses Sprotty as graphics engine here for the models. And this, of course, is for modeling using the properties and having a palette. So again, these are technologies that we use under the hood. And the holistic approach, language engineer uses a textual editor to design language, uses a button. You can see it here because it's too small, but to upload it. And later in the process, the domain expert can, by a push of a button, deploy a new modeling editor, like a textual or language editor, but with a canvas, and use that language. So, live metamodeling. If you create a language, you always want to try to use it. And up here we have the abstract syntax like node, edges, and so on that we specify textually. And if we change something here, we also want to, without closing, opening, or something else, directly have the response in our canvas where we use the language. So this is where we specify the language. This is where we use it. That means the palette should be extended, or maybe if we delete a node, it should be eliminated from the palette, the node, for example. And this also should be the case for the styling for our concrete syntax. If we change something here, like a background color of an element or the shape or some other appearance, we would like to have it reflected inside the canvas directly on all the elements. And these are the challenges, updating the canvas palette and appearance of the elements. But in our abstract syntax, or the specification of the abstract syntax, our MGL, we also can specify containments, like which node can contain which other nodes and so on. And we also want to reflect it, have it reflected here, like these containments. But this is also the case for edges. Nodes can be specified, incoming and outgoing edges, which types of edges are allowed, how many of them. And yeah, we also, if we change something in the meta model, we also want to have it reflected in the behavior while we use that language. And yeah, there are also update anomalies. What if we created a node that is later not part anymore of the language? We also want to have this reflected in all this. And how we done it? We used an internal structure that we call the meta specification. It's like the intersection of all possible graphical languages that we support, like very intuitively graph types, node types, edge types, and so on, and all the properties like constraints, strings, attributes. Yeah, you get the picture. But also inside this whole model, the styles and appearances, and all interconnected. And not only for one language, because we also want to support compositions of languages, like maybe you want for two specific use cases, two languages that you want to compose. We also want to have them all in one. Yeah, and this is how we did it. And an additional thing that this structure can do, or in the creation of this structure, we resolve constraints and attributes that are part of polymorphy. Like if a node extends another node, or there is an abstract node in between, we want to only have concrete types in here, no abstract types. Like abstract types are eliminated, and all these properties, which can be part of inheritance, are taken into the concrete types. Yeah, this is for the syntactic stuff. Now to the semantic stuff, how we execute code. This is like a graph model, or you could also see here a node or something else that is specified, and we annotate it with actions, hooks, and events, like here it is generator action, because we want to specify a generator for this graph model. Graph model in this case means graphical language, because we see such a graph model as a language. And yeah, what we do here, inside this annotation, we put a value which corresponds to a TypeScript class that can be implemented and need to be here inside this special folder. It's a languages folder. It's just called like this, which I come a few slides later to. And what happens here is if we now have such a graph model open and we push the generator button, it should execute this code, and we get a response in the GUI, and in the end we get the generated output here in the file system, for example. And yeah, the challenge here is we want to have it live. If we change something in the code, in the TypeScript code, we directly want it reflected in the next click on the generator button. And how we realized this was also very simple. We just use a file watcher on this languages folder, where we have all our stuff in it and all our TypeScript classes. Under the hood, we also use some transpilation to JavaScript and just use the JavaScript GLP interpreter to directly update it inside the running system. So it's an internal real-time update of the code. And yeah, this was for the semantic part. Again, to this languages folder, it's like a hook in point on the file system to where we put all our languages. Like in this case, we have an example language, abstract syntax, our MGL file. We have the concrete syntax, the styling for these nodes, and some TypeScript classes, for example, and which are referenced inside here. So we have all our syntax and semantics, our languages, inside this folder, and from that on, we can run the file watcher and so on, and just see for updates. And this is perfectly for language engineers, because they want to create the languages, they want to modify all of this. And and access this languages folder, but should not be the case for the domain expert. That's why we access restrict this folder and hide it outside of this workspace. So now for the demo of this all. This is Cinco Cloud, the running instance on cinco.cloud. And you can create an account, and then it looks like this. We have this project and organization management. You also have a profile. And by this push of a button, I'll now create a new workspace. And this workspace is now spawning in the background. And then it takes some seconds. There you have some other info. There are a few participants who have also access to this workspace. But when the time comes, the workspace is ready. This workspace, of course, is based on Eclipse Thea. And the first time you started with an empty workspace, you get this project initializer where you can directly create a language like, for example, we just call it Langdev. And all files that, or more models that we can now create have the ending, file ending Langdev. This is a simple language that is created, just an exemplary. We have a graph model, so our language. We have nodes, node types of the type SumNode, which is contained in this graph model and has an attribute label. I hope it's big enough. And we also have an edge that we can use as incoming or outgoing edge on this SumNode. So as soon as this language folder has these syntactic files, we just can create a model. I call it example. And we directly have access to a canvas where we can use that language. And also side by side with that syntax of the metamodel. And now if we create a new node, like SumNode 2, it should be updated as soon as it is part of the language. Like if we now add SumNode 2 here, the palette is updated and we can directly use SumNode 2 here. So this is also possible for the edges and so on. And now if we want to make them look a little bit different than just a white blob, we can, here, this SumNode has the style labeled circle with the parameter of the attribute. So if we change this attribute, which is here, like hello, which is now a little bit bright here inside this white ball, this is referenced here. And here is the input parameter, and it should be shown in a text inside an ellipse. And if we now change the appearance of the ellipse, which is referenced here, like this, it is also directly reflected in the styling. So we can live design our graphical languages. So this was a fairly simple example. I now want to show you a little bit more sophisticated but playful example. This takes a few seconds. And in this folder that you now see, we have, again, it's the languages folder, which has two languages. Pizzeria we now ignore, we just need Halloween. And if we create a Halloween model like this, we can create, it's like a level editor for a simple 8-bit game. It is fairly simple. It's a Halloween game. It can contain only one level because it's my restriction. This level can contain at least only one player and multiple game objects, which are obstacles, items, enemies, and so on, which also have some attributes like items can heal. Skull is an enemy that has an attack and speed, and so on. And now, if we create a level, it's, for example, just like this, and we can place our player onto it. And what you may see is we also have some, an annotation here that is called hook, which references a TypeScript class inside our semantic folder here in the languages folder. Game object hook is called the class. It's just simply to fix the position if a node is created of the type player that is, like in the old games, only placed on one of the tiles. And now if we also create a skull here, now we can run the generator and directly use the preview view to show the game. So the game is fairly simple. You just kill all enemies and you win. And but what's interesting is that now if we run the generator, it outputs some text and does something in the background, and in the end it says game generated. And if we change it like game generated at Langdev and generate the code again, it directly updates stuff. And one interesting little other thing to make it a little bit more like a live game engine, there is also another hook. Every time something in the graph model changes, we want to trigger the generator. If I now make this hook accessible, now if we, for example, add another skull, it should be directly updated, and we have another skull that we need to finish off, and then we win. So this is just a little example where we change live the semantics and syntactic parts of the graphical languages and use, like in a holistic approach, all three levels, meta level, modeling level, application level, inside one IDE. And thank you very much for your attendance. If you have any questions, sorry I forgot it in the beginning, you can use this code. And this is our GitLab repository. We're always looking for people that can help us out. And you can also try it for yourself in here at Cinco.Cloud. Thank you very much.
Yes, thank you. Are there any questions? Yes, please.
This live metamodeling looks really nice when you want to try out things. I was curious, what happens if you break stuff?
In the metamodel?
Yeah, for example, I have a nice model, and now I make a change in my metamodel, and it updates like a model.
Yeah, it looks like this. So, because the grammar, under the hood, we pass it with Langium, and if the AST is not correct anymore, it falls back to what we generated. In this case, it's a little bit broken. It's like the correct language, but broken. Because in this case, you specify here all the containments. And for example, now because it's wrong, it has no containments anymore. So this language still exists, this graph model, but the containments are not part of the language anymore. And but if you, for example, only, let's say only the player is, one moment, only the player isn't part anymore, like this, it should So if the rest is correct, only the player isn't part of the language anymore, and this should be in some way visualized, so that it can be.
Is there a way to revert back?
Yeah, of course.
You do it save intermediate state there, right?
Yeah, yeah. For example, it's now not called play anymore. Yeah. For example, this way. This does.
Also for the model level?
Also, the model stays the same. It holds all the false data, because you don't want to lose it. Like if you would have closed it and reopened it again, there would still be the red thing that it's not part, but it still has the type in its ID and all the other information.
Thanks.
Maybe just from my side, a direct follow-up question. Is it possible to directly transfer the changes on the metamodel level to the model level? For example, this was just a refactoring of the name of the type or something like this. I think it's pretty, just from thinking, it should be pretty easy to just say, and now apply to my active model.
Yeah, this would be cool. Not present.
No problem. Further questions? Yes.
In which scenarios have you used this so far?
This?
So the general Cinco Cloud, like for your own use, or in with some other people at the university, or in some industrial settings, or?
As far as I know, no industrial setting. The MGL and MSL is like, I think, 10 years old in Dortmund, in Germany. And there was it was used to create a graphical GPL called DIME, which was a graphical DSL to create full stack web applications, and a full stack web application was created from this for the Springer Verlag from Germany as for a conference system. So this was the biggest application for all of this. But we usually have more experimental, smaller languages like this.
Okay. Yes, please.
Do you have support for manual changes in the generation code?
Can you repeat this?
So you're making a metamodeling model, and you're producing some running artifacts from that, if I understand correctly.
Yeah, in this case, yeah.
Change those artifacts manually, or you're regenerating for the model always from scratch?
From the step from this metamodel to the metamodel of this graphical language server, if you want to call it like this, is internally we read this and transform it internally to this internal meta specification that I showed. But in the case of this modeling to this, it's a generated file. I think it's just called config.js, if you mean, if this answer.
It's like interpret.
Yeah, right. Mm-hmm. Right.
Okay. No further questions? Then let's thank the speaker again.
Thank you.